Hello there, and welcome. I'm glad you've arrived tonight. Perhaps you've had a long day, or maybe you're searching for something quiet and vast to wander through before sleep. Either way, you are here, and that is enough. You don't need to do anything but rest. Let your shoulders ease, your breath slow, and your thoughts drift. Tonight, we're not just gazing at stars. We're entering their story. A story that is both older than humanity and woven into every part of who we are. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath, let your day drift away, and let's travel together into the quiet corners of the universe. When you step outside on a clear night and look up, the first thing you notice are points of light scattered across the sky. To your eyes, they seem small, delicate, like pinholes in a dark curtain. They appear as faint glimmers, some steady, some flickering with gentle persistence. But each of those specks is far more than it seems. Every visible star is a sun, vast and radiant, releasing unimaginable energy into the emptiness of space. Our own sun is one such star, close enough to flood our world with warmth and light. The stars we see at night are distant suns, burning across millions or even billions of years, their glow surviving vast journeys through the dark to reach us. They look fragile, but in truth they are colossal, fierce engines of creation. For as long as people have existed, stars have been our companions. Before maps or compasses, they told us where we were. Travelers and sailors traced their paths across seas, guided by the fixed stars, their courses written in the heavens. Farmers looked to the seasonal rise and fall of constellations to mark the cycles of planting and harvest. Entire mythologies grew around their arrangements, each culture weaving its own stories into the sky. To some, stars were gods or ancestors. To others, they were fires kindled by divine hands, or windows to the worlds beyond. Even in our modern age of satellites and digital clocks, the stars still invite us to pause, to look up, and to wonder. And yet, what you see with your eyes is only the faintest fraction of what exists. On the clearest night, far from the haze of cities, you may glimpse a few thousand stars. To us, that feels like an ocean of light, but it is hardly a drop in the cosmos. Astronomers estimate that the Milky Way alone contains over 100 billion stars, and beyond our galaxy lie billions upon billions more. The night sky is not a map of all that is, but a small keyhole view. Most stars are hidden from us, lost in distance, obscured by dust, or too faint for human sight. What we see is only a whisper of the true vastness, yet that whisper has always been enough to stir us. There is something in our nature that responds to these lights, as though some ancient memory recognizes them. Perhaps it is because our lives have always depended on a star. The sun sustains us, cradles us, and shapes every rhythm of our days. Perhaps it is because, in a deeper sense, we are made of stars. The iron in your blood, the calcium in your bones, the oxygen in your breath, all were forged long ago in the furnaces of stars that lived and died before the earth was formed. To look at the stars is, in some way, to look at ourselves. It is easy to forget this when we see them as so small. Their distance disguises them. Even the nearest star beyond the sun, Proxima Centauri, is more than 4 light-years away. That means its light, traveling at nearly 300,000 kilometers per second, takes more than 4 years to reach us. When you look at it, you are not seeing it as it is, but as it was years ago. In truth, every star you see is already part of the past. The night sky is a time machine. each point of light a memory carried across unimaginable gulfs of space. Still, they seem eternal. People from thousands of years ago looked at many of the same stars you can see tonight. Constellations they once named still glitter in familiar shapes, binding us across centuries. Yet stars, like all things, have lifespans. They are born, they live, and they die. Some will swell into giants and end in brilliant explosions. Others will fade slowly, cooling into quiet embers. But even in their death, they leave behind the raw materials for future stars, planets, and life. Stars do not just shine, they build, they transform, they pass their light forward into new generations. Imagine for a moment the stillness of lying beneath them. The earth turns, and the stars appear to wheel gently across the night. Constellations rise and set. The North Star holds steady, a beacon for those who search for direction. To us, the stars feel permanent, steady markers of time and place, and yet they too move, orbiting the heart of our galaxy, drifting in slow patterns that take millions of years to unfold. The stars above you are not fixed, only patient, shifting so gradually that generations can live and die without noticing. Even the heavens flow. And so tonight, you are invited to drift with them, to let yourself be carried not by the demands of the day, but by the quiet pull of curiosity. Each star you notice has a story, written in light, in motion, in age. Some are young and hot, blazing blue. Others are old and red, dimming toward their eventual end. Some shine alone. Others orbit companions, dancing in pairs or trios. Each is part of a greater tapestry, a cosmic sea that stretches farther than we can see, yet close enough that its glow finds your eyes here and now. The stars have been our calendar, our compass, our myths, and our teachers. They remind us of our smallness, but also of our connection to something far larger. When you breathe in, when you rest, you are not separate from them. You are part of the same unfolding story, born from the same matter, carried by the same universe. Tonight, as you let your body grow heavy with rest, you can imagine yourself not beneath the stars but among them, floating, quiet, weightless, surrounded by suns beyond counting. You are safe here, in this endless expanse, where wonder is as steady as starlight and as calming as night. When you look at a star, you see a quiet light against the dark. To the eye, it seems gentle, even fragile, as though you could reach out and brush it away like dust. But the truth of a star is nothing so delicate. A star is a furnace, an immense and steady fire, a cauldron of unimaginable heat and pressure. At its heart, atoms are pushed so close together that they fuse, transforming into new elements and releasing energy that travels outward across millions of kilometers of plasma until it escapes into space as light. What looks like a flicker in the night is in reality the glow of nuclear fusion, steady and relentless, a process that has burned for billions of years and will continue for billions more. Stars are built from hydrogen, the simplest and most abundant element in the universe. Left to itself, hydrogen drifts quietly as gas, thin and cool, spread across vast clouds. But gravity gathers it, pulling atoms together, compressing the gas until the pressure grows immense. At the very center of a star, the conditions become extreme enough that hydrogen atoms no longer resist. Their nuclei merge, forming helium, and in the act of fusing, a tiny portion of their mass is converted into energy. That energy is what shines from every star, what warms planets, what reaches your eyes when you look into the night. It is Einstein's equation, E equals mc squared, unfolding endlessly in the depths of stellar hearts. This energy is not released in a flash, but in a balance. Gravity pulls inward, trying to collapse the star under its own weight. Fusion pushes outward, creating pressure that resists the crush. For as long as the two forces remain equal, the star lives in stability, its light steady, its shape constant. It is a cosmic hearth, neither exploding nor imploding, but burning at just the right intensity to endure for ages. If gravity ever gains the upper hand, the star collapses. If fusion overpowers gravity, it tears itself apart. But when the two forces are matched, the result is a long, stable life, a star shining with quiet persistence across the void. The temperatures inside a star defy comprehension. At the surface, even the relatively gentle warmth of a star like the Sun reaches nearly 6,000 degrees Celsius. At its core, where fusion rages, the temperature climbs above 15 million degrees. In the most massive stars, that number rises into the hundreds of millions. At these scales, heat is not simply warmth as we know it, but energy so intense it strips atoms of their electrons, reduces matter to plasma, and allows the impossible two positively charged nuclei, which should repel each other, to collide and merge. The light that escapes from such fury seems soft to us, but it began in a crucible of unimaginable power. Despite this raging fire, stars do not burn out quickly. Their very size ensures their longevity. A star is not consuming fuel the way a flame eats wood. Instead, it is fusing atoms at the rate demanded by balance. Small stars, such as red dwarfs, burn their hydrogen slowly, sipping their fuel across trillions of years. They are faint and dim, but they endure longer than any other stars in the universe. Larger stars, by contrast, blaze brilliantly, pouring out energy millions of times greater than the sunday, but their brilliance is costly. They consume their hydrogen at a furious pace, exhausting their lifetimes in only a few million years. The difference is vast. Some stars live long enough to outlast galaxies, while others are gone in what feels like an instant of cosmic time. The energy a star produces is immense, even when measured against our human scale. In a single second, the Sun emits more energy than humanity has consumed in all of recorded history. It radiates in every direction, across the spectrum, from visible light to ultraviolet and X-rays. Most of that energy streams into the emptiness of space, uncounted, unseen. Only a tiny fraction reaches Earth, yet it is enough to drive winds and currents, grow forests, sustain oceans, and allow life to flourish. Every sunrise is powered by fusion in the Sun's core, a reaction that began 4.5 billion years ago and will continue for billions more. And still, stars are not infinite. The balance they hold is temporary, though on timescales so immense it feels eternal to us. Our Sun is midway through its stable life, a main sequence star that has been shining steadily for nearly 5 billion years and will continue for about 5 billion more. When its hydrogen runs low, gravity will begin to win. The core will contract, heat will rise, and new stages of fusion will ignite. It will swell into a red giant, vast enough to engulf the inner planets. Eventually, it will shed its outer layers, leaving behind only a dense white dwarf, glowing faintly in the dark. In this way, every star carries its ending within it, an inevitable conclusion written in the balance of fuel and gravity. To think of stars as furnaces is accurate, but it is also incomplete. They are not simply engines of energy, but architects of matter itself. The hydrogen and helium that begin in their cores are transformed, step by step, into heavier elements. Carbon, oxygen, nitrogen, silicon, iron, all forged in the fires of fusion and spread into the galaxy when stars die. Without these processes, there would be no rocky planets, no water, no air, no life. A star does not simply shine, it creates. It is a workshop of atoms, a quiet factory where the universe turns simplicity into complexity. Yet for all their power, stars feel strangely personal to us. We describe them as guides, as keepers of time, as symbols of permanence. Perhaps it is because, in a deep sense, we know we are tied to them. They are our ancestors, Every breath you take carries oxygen that was born in a star. Every beat of your heart is powered by iron shaped in a stellar furnace. Stars are not distant in truth. They are within us, their story written in every cell of our bodies. So the next time you look at a star, remember what you are truly seeing. It is not a flicker or a pinprick of light, not a jewel hung against the night. It is a colossal furnace, bound by gravity, burning with the quiet rhythm of fusion. It is a balance of forces, steady and enduring. It is a cosmic hearth, patient, generous, and ceaselessly creative. And through its light, across the cold expanse of space, it whispers a truth both simple and profound. Stars do not just shine in the sky, they shine in us. In the darkness between the stars, vast clouds drift in silence. They are made of gas and dust, invisible to the human eye but immense in size, stretching across hundreds of light years. These are molecular clouds, the coldest places in the galaxy, where hydrogen lies in deep slumber only a few degrees above absolute zero. For millions of years, they drift quietly, stirred by faint turbulence, shaped by distant supernovae, nudged by passing stars. Then, in some regions, gravity gains the advantage. The gas begins to gather, atoms pulling atoms, the balance tipping slowly toward collapse. What begins as a quiet drift becomes the first step in the birth of a star. As gravity pulls the cloud tighter, the density at its center grows. The material falls inward, creating knots that swell into cores. These dense regions are hidden from sight, wrapped in veils of dust that block visible light. Yet inside them, pressure and heat rise with every passing moment. A protostar begins to form at the heart of the collapse, a seed of light not yet lit, surrounded by a swirling disk of gas and dust. This disk is an accretion flow, matter spiraling inward, feeding the growing mass. The protostar itself flickers faintly, warmed not by fusion but by the energy of falling material, by the gravitational heat of gas colliding as it gathers. In these hidden chambers of space, the promise of a new star takes shape. The process is neither quick nor simple. Over hundreds of thousands of years, the protostar continues to draw in matter, growing heavier and hotter. Its surrounding disk glows faintly in infrared light, invisible to our eyes but seen by telescopes. Jets of material may burst from its poles, streams of gas shot outward as magnetic fields twist and snap, balancing the inflow with outflow. The system is chaotic, but every chaotic movement brings the star closer to ignition. Deep in the core, the density reaches the threshold where hydrogen atoms are pressed so close they begin to fuse. The moment this happens, a transformation occurs. The protostar becomes a true star. Light that once came only from falling matter now streams outward from the fire of fusion, and for the first time the star shines with its own power. Stars are not born alone. In these vast molecular clouds, collapse does not happen in isolation. Many regions fragment, forming clusters of protostars that grow together, bound by gravity. Some will survive as companions, orbiting each other for billions of years. Others will drift apart, scattered across the galaxy by the movements of their cluster. When we look at young regions of the sky, such as the Orion Nebula, what we see are cradles of hundreds, even thousands of stars being born together. They are siblings in light, their shared origin etched into their chemical fingerprints and motions, even if time will scatter them far from one another. The imagery of a nursery is not far from the truth. Within the womb of dust and gas, stars are cradled, protected from the glare of the wider galaxy. These clouds shelter them, slow the rush of radiation, and provide the material needed to feed their growth. To peer into them is to witness creation in its earliest stages. Radio and infrared telescopes pierce the veils, revealing glowing filaments, knots of collapse, and faint embryonic stars just beginning to shine. The light that escapes is delicate, filtered through dust, as though the stars are whispering rather than shouting their presence. It is only as the clouds disperse, blown away by the winds of newborn suns, that the cluster emerges into clarity, a field of fresh light scattered across the dark. The timescales of stellar birth are vast compared to human life, yet fleeting in the context of the universe. A star spends millions of years forming, but once fusion begins, its path stabilizes into billions. It is as though the early years are a long and restless childhood, full of turbulence and gathering strength, leading at last to maturity and balance. During this time, planets may begin to form in the accretion disk, grains of dust sticking together, growing into pebbles, rocks, and worlds. By the time the star steadies into the main sequence, it may already be surrounded by companions of stone and gas, a solar system cradled alongside its own birth. Even our sun began this way. Long before Earth existed, the sun was a protostar in a crowded nursery, drawing in gas, casting off jets, surrounded by siblings that have long since wandered away. The cluster dissolved over time, leaving our star to travel the galaxy alone. But somewhere out there, those lost siblings still shine, carrying the same chemical signatures of origin, families scattered across space. Every star you see in the night sky tells a similar story. None was born in solitude. All began in clusters, wrapped in clouds, brought into being by the same quiet collapse of matter into fire. The life that emerges from these clouds is astonishing in scale. Each star represents the transformation of something diffuse and invisible into a radiant point of light. A gas cloud that once appeared as emptiness to the human eye becomes the birthplace of suns capable of warming planets, shaping galaxies, and seeding future generations of stars with the elements they create. It is a reminder that the void is not truly empty. It carries potential, waiting for the right moment to fall inward, to ignite, to shine. When you look up and see the stars, it is easy to imagine them as eternal, as if they have always been there. But each one was once hidden, veiled in darkness, slowly gathering its strength. Each one began in a cradle of dust, nurtured by gravity, ignited by fusion. The stars are not permanent fixtures in the sky. They are stories of becoming, quiet fires that began in clouds too vast for us to comprehend. And every light you see is proof that even in the deepest darkness, creation continues. When a star is born, it is rarely alone. Deep inside, molecular clouds, collapse does not occur in isolation, but in many knots at once. Gravity gathers gas into numerous cores, each of which kindles into its own protostar, and together they rise from the darkness as a cluster. These stellar siblings begin their lives side by side, surrounded by the remains of the cloud that formed them. They share the same chemistry, the same age, the same origin. Though their paths will eventually scatter them across the galaxy, for a time they are family, glowing together in a crowded nursery of light. Open clusters are among the most beautiful remnants of these shared beginnings. The Pleiades, often called the Seven Sisters, is one of the brightest and most famous examples. To the naked eye, it looks like a tiny dipper-shaped group of stars, faintly veiled by a bluish haze. In reality, it contains over 1,000 members bound loosely by gravity. The haze is dust reflecting the star's light, a reminder of the cloud that once cradled them. Open clusters like this are young on a cosmic scale, often only a few 100 million years old, and eventually their bonds weaken. Encounters with other stars, the pull of the galaxy's tides, and the simple fact of their loose arrangement mean they will drift apart, leaving their stars scattered and unrecognizable as kin. Yet, for as long as they endure, they remain among the most striking sights in the night sky, shining reminders of how stars come into the world together. Not all clusters are so fleeting. Globular clusters, those densely packed, ancient spheres of stars, orbit far beyond the galactic disk, like glowing lanterns at the edge of the Milky Way. Each contains hundreds of thousands, sometimes millions of stars, crammed so closely together that their light merges into a golden haze when seen through a telescope. These clusters are among the oldest objects in the galaxy, survivors from a time more than 10 billion years ago when the universe itself was young. Unlike open clusters, globular clusters endure for eons because their stars are bound tightly, packed into a spherical ball that resists disruption. They circle the Milky Way in the halo, far above and below the galactic plane, ancient companions to the spiral that has grown younger and brighter around them. To gaze upon one is to look at a fossil of cosmic history, a family of stars still together after almost the entire age of the universe. Our own sun was once part of such a family, though not as grand as a globular cluster. It was born in an open cluster, alongside hundreds or perhaps thousands of siblings. They would have shone together for a time before dispersing, flung apart by gravitational tides until the sun was left to travel alone. Somewhere across the Milky Way, those lost siblings still burn, carrying with them the same chemical fingerprint, the same ancient dust in their cores. Astronomers today search for them, hoping to find stars that share the sun's composition and motion, stars that were cradled in the same nursery before the cluster dissolved. Finding them would be like discovering long-lost family members in a galaxy of strangers, kin hidden among the billions of lights. Clusters are not only families but also laboratories of cosmic truth. Because their stars are born together, they are the same age and composition, yet each may differ in size and mass. Studying them allows astronomers to understand stellar evolution, to compare how stars of different weights live out their lives under the same conditions. A massive star may burn hot and die quickly, while a smaller sibling smolders gently for billions of years. Clusters hold the entire spectrum of stellar fates in a single glance, from bright blue giants to faint red dwarfs, each a different path carved from the same origin. They are nature's way of writing a shared beginning into countless possible endings. There is poetry in how these families scatter. When the bonds of an open cluster finally loosen, the stars drift outward, carried on the great currents of the galaxy. Over millions of years, they will be unrecognizable as siblings, scattered across spiral arms, swept into new neighborhoods of stars. Yet though they part, they are never truly severed. Their origins remain coded in their chemistry, their ages, and their faint motions. The galaxy itself becomes a tapestry woven from countless such dispersals, clusters dissolving into its disk, their children drifting far but always leaving traces of where they came from. To imagine a star cluster is to imagine both intimacy and eternity. In the core of a globular cluster, stars are so crowded that their skies would blaze with hundreds of times more starlight than our own. Night would never truly fall there. Yet beyond the halo, globulars remain steady, holding their stars tightly bound for billions of years. Meanwhile, open clusters, loose and fragile, scatter after only a fraction of that time, their members slipping quietly into the wider galaxy. Each kind tells its own story about gravity, endurance, and the fragile bonds of stellar kinship. The stars in your sky tonight may carry such memories. Some may have been born together in a cluster long ago, still moving faintly in parallel across the heavens. Others may have left their siblings behind billions of years ago, their family now untraceable. And our sun, once cradled in its own cluster, continues alone, orbiting the galactic center with no siblings nearby, though its lost brothers and sisters still shine unseen, scattered across the spiral. To think of clusters is to think of family on a cosmic scale, stars that begin their lives together, sharing light, heat, and motion, before drifting into the vastness, each carrying a piece of their shared history. Some stay bound for eons, enduring as ancient orbs of light. Others scatter swiftly, leaving only the faintest fingerprints of their kinship. Yet in both cases, they remind us that the galaxy is not built on isolation. It is a place of gatherings and partings, of families formed and dissolved, of connections both fleeting and eternal. And when you look up at the Pleiades on a cold night, or when you glimpse the golden haze of a globular cluster through a telescope, you are seeing more than stars. You are seeing families, born together, still bound or long dispersed. You are seeing the truth that no star is ever truly solitary at its beginning. Every light carries the memory of a cradle, of siblings scattered across the galaxy, of bonds written in gravity and in light. When you gaze at the night sky, it may seem that all stars shine with the same silver light, twinkling like beads of frost on a black curtain. But if you look more carefully, or if you give your eyes time to adjust in the stillness of a clear night, you will begin to notice a secret woven into their glow. Some stars burn with a faint orange tint, others with a soft golden warmth, and still others with a piercing bluish white that seems sharper, colder. Stars are not all the same. Their colors are clues, whispers of the fire within, telling us how hot they burn, how massive they are, and how long they will live. The science of starlight divides them into a spectrum of classes, each with its own hue and temperature. Astronomers sort them with the letters O, B, A, F, G, K, and M, a sequence that at first feels like a puzzle, but reveals a gradual shift from the hottest and bluest stars to the coolest and reddest. O-type stars are the titans of heat, searing with surface temperatures that exceed 30,000 degrees Celsius, their light a fierce, luminous blue that slices through space. At the other end, M-type stars are cooler, their surfaces only a few thousand degrees, glowing in dim shades of orange and red. Between these extremes lie the rest, including the G-class star we know most intimately. Our sun, golden and steady, sitting somewhere near the middle, neither the hottest nor the coldest, but just right for the life it nurtures. To understand a star's color is to understand its temperature. Heat changes the nature of light, bending it toward the blue when it blazes most fiercely and toward the red when it glows more gently. Blue stars, like O and B types, shine so hot and bright that they often overwhelm the skies around them. They live fast, burning through their fuel in only a few million years before collapsing into spectacular ends. Their brilliance is short-lived, but dramatic, like fireworks against the slow backdrop of the universe. Red stars, by contrast, are the patient ones. Many are small, cool, and steady, glowing faintly for billions, even trillions of years. Their light may be dim compared to their hot cousins, but their longevity ensures they outlast nearly everything else in the cosmos. In between, stars take on a rainbow of shades, each class carrying its own balance of heat and time. A-type stars gleam white with a hint of blue, like Sirius, the brightest star in our night sky. F-type stars glow pale yellow-white, warmer than the sun but cooler than the searing blues. G-type stars, like our sun, radiate with the warm yellow that has nurtured life on Earth for billions of years. K-type stars, sometimes called orange dwarfs, burn slightly cooler, their amber light steady and calm. And M-type stars, the faint red dwarfs, make up the vast majority of stars in the universe, tiny embers glowing in the dark, often invisible to the naked eye but scattered everywhere like dust in the wind. When you look at a star's color, you are not only seeing its temperature, you are glimpsing its life story. Blue stars are young, born from vast clouds of gas and dust, burning with intensity that cannot last. Their lives end violently, in explosions that scatter heavy elements across space. Yellow and orange stars live longer, carrying on through quiet, steady ages. And red dwarfs, the smallest and coolest, are so thrifty with their fuel that they may live hundreds of billions of years, longer than the universe itself has yet existed. They are stars of patience, guardians of time, destined to glow gently when all the brighter ones have burned out. Brightness can be deceiving. To our eyes, stars may all look white because the subtle variations of color are drowned by distance and atmospheric haze. Yet through a telescope or even binoculars, the hues begin to emerge more clearly. Betelgeuse, the great red supergiant in Orion, glows with a warm, ruddy light. Rigel, its neighbor in the same constellation, blazes blue-white, a hot giant many times brighter than the Sunday. Together they stand as a living comparison of stellar extremes, two stars born of the same region but fated for very different paths. The differences in color and temperature shape not only how stars live, but also how they end. A blue O-type star will swell into a red supergiant, then collapse in a supernova, leaving behind either a neutron star or a black hole. A golden G-type star like the Sun will swell into a red giant before gently casting off its outer layers, leaving behind a white dwarf. And a red M-type dwarf may never go through such drama at all, simply fading slowly over trillions of years into a cold, dark ember. In the language of color, the destiny of each star is already written, glowing faintly across the night. When astronomers spread the light of a star into a spectrum, they can read more than just its hue. They can see the fine lines etched by elements, signatures of hydrogen, helium, calcium, and iron. These lines deepen the story told by color, revealing not only how hot the star is, but what it is made of, how it has evolved, and what may lie ahead. The spectrum is like a fingerprint, unique to each star, but its overall color remains the most immediate clue, a visible key that even the human eye can glimpse without instruments. There is poetry in the way color reveals both power and fragility. Blue stars shine with enormous energy, but fade quickly, like torches in the wind. Red stars glow faintly but endure beyond imagination, like embers that never go out. In between lie the stars that balance brightness and longevity, suns that can nurture planets, warmth, and perhaps life. Our sun, golden in its steadiness, is one of those, and its light is the reason you can look up tonight and wonder at the others. Every star you see carries a story of heat and time, told in color. The faint orange of Aldebaran, the white blue of Vega, the steady gold of the Sun, the deep red of Betelgeuse. They are pages of a great stellar spectrum written across the sky. You may not notice their hues at first glance, but once you know how to look, the night sky becomes a rainbow, a quiet parade of temperature and age glowing far above the earth. And so, when you tilt your head back beneath the stars, let your eyes linger. Let them adjust to the darkness until you begin to see the subtle differences, the faint blush of one, the icy glint of another. In those colors lies the truth of what stars are. Cosmic hearths burning at different intensities, some fierce and brief, some patient and enduring, all of them carrying the signature of their heat in the light they send to you. When you step outside on a quiet night and tilt your gaze upward, the stars seem to sprinkle the heavens evenly, a simple scattering of points across a dark canvas. But behind those distant lights lies an astonishing variety of size and scale. Some of the stars you see are so enormous that if placed at the heart of our solar system, their swollen surfaces would extend past the orbit of Jupiter. Others are so small that they are only a little larger than the planet itself, faint and easily overlooked, yet they make up the majority of stars in the universe. The night sky is not a uniform quilt of identical suns. It is a story of extremes, where the smallest stars glow with quiet endurance and the largest ones blaze with furious intensity before vanishing in cataclysm. The most common stars of all are the smallest, red dwarfs. They make up nearly 3/4 of the stars in the Milky Way, yet most cannot be seen with the naked eye because their light is so faint. A red dwarf is small, often less than half the mass of the Sun, with a surface temperature that gives it a soft reddish glow. Despite their modest size and dim appearance, they possess an extraordinary quality patience. Because they are thrifty with their hydrogen fuel, red dwarfs burn it so slowly that they can shine for hundreds of billions of years. The universe itself is not yet old enough for even one red dwarf to have lived out its full lifespan. These tiny embers are the marathon runners of the cosmos, enduring far beyond the brighter, flashier stars that dominate our sky. Their very smallness grants them stability. In larger stars, the balance between the inward pull of gravity and the outward pressure of fusion is a delicate one, often unstable, leading to violent ends. But in red dwarfs, the forces find a steady equilibrium. They do not waste fuel with the same reckless abandon as giants. Instead, they sip slowly from their reserves, glowing gently in shades of orange and crimson. Some astronomers suggest that these humble stars may be the most promising hosts for life-bearing planets, not because they are dramatic or warm, but because they last long enough for life to take root and evolve without interruption. At the other extreme are the giants and supergiants, stars that dwarf even the mighty Sunday. Betelgeuse, the red supergiant in the constellation Orion, is so vast that if it replaced our Sun, its outer layers would swallow Mercury, Venus, Earth, Mars, and even the asteroid belt. Its surface is cooler, glowing with a ruddy hue, but its sheer size makes it blaze hundreds of thousands of times brighter than our Sunday. Betelgeuse is nearing the end of its life, swelling outward as its core struggles with the exhaustion of fuel, a reminder that great size often comes with great instability. Someday, perhaps soon in cosmic terms, Betelgeuse will explode in a supernova, outshining the entire galaxy for a brief moment before fading into a remnant. Nearby in the same constellation lies Rigel, a blue supergiant. Unlike Betelgeuse, Rigel burns with an intense heat, its surface tens of thousands of degrees hotter than our Sunday. It radiates with a piercing blue-white brilliance that makes it one of the most luminous stars visible from Earth. Rigel is far more massive than Betelgeuse, but its youth and temperature give it a different character. It is a furnace burning through its fuel at an astonishing rate, destined to live a short, brilliant life before meeting a similarly violent end. In Rigel's light, you can see the other side of stellar gigantism, beauty that is sharp, searing, and impermanent. The range of sizes in stars is staggering. The smallest red dwarfs are not much larger than Jupiter, a planet rather than a star by every other measure but one. They sustain fusion in their cores. Just above them lie the brown dwarfs, sometimes called failed stars, too small to ignite full fusion, glowing only faintly in infrared. At the other end of the scale are the hypergiants, rare behemoths that make even Betelgeuse seem modest. Some of these monsters shine millions of times more brightly than the sun, their outer layers unstable and shedding material into space like clouds of smoke from a roaring fire. They are few in number but dominate their neighborhoods, sculpting their surroundings with winds, radiation, and eruptions. This contrast between the smallest and the largest stars shapes the rhythm of the galaxy. The little ones live quietly, enduring across cosmic ages, their light faint but steady. The big ones live dramatically, often forming in clusters where their intense radiation and supernova explosions stir the birth of new stars around them. One kind offers longevity, the other creativity through destruction. The Milky Way is built from both, the quiet embers and the roaring furnaces, each playing a role in the cycle of matter. Our sun sits in the middle, a balance point between extremes. It is not the largest, not the smallest, but steady and long-lived, burning through its hydrogen reserves with measured patience. It will shine for billions of years more, long enough for life to rise and evolve on Earth, long enough for civilizations to look upward and wonder. But compared to the quiet glow of red dwarfs, the sun is already burning through its life at a quick pace. Compared to the short-lived giants, it is an elder statesman, unhurried and calm. Its middle ground makes it both ordinary and rare, a fortunate kind of star that offers stability without haste. The destiny of a star is written in its size. Small stars fade slowly into faint white dwarfs, cooling embers that may outlast galaxies. Massive stars collapse in spectacular explosions, scattering heavy elements into space, seeding new generations of stars and planets with the material for worlds, oceans, and even life. Between them, stars like the sun swell into red giants before shedding their outer layers and leaving behind compact cores. Each pathway is different, yet all begin with the same process of fusion, the same balance of gravity and heat, the same light sent out across space to reach our eyes. So when you look up, remember that the sky above you is not filled with identical pinpricks. It is filled with lives in progress, some barely larger than planets, glowing with endless patience, others vast and turbulent, destined to die in fire. The stars are companions not only in beauty but in diversity, each one a variation on the theme of light. The smallest stars keep secrets of the far future, glowing still when galaxies have changed beyond recognition. The largest stars mark their presence briefly, leaving behind brilliant echoes of their passing. And between them, our sun glows with a light steady enough to nurture you here and now, in this fleeting moment, beneath a sky stitched together by embers great and small. Every day begins with it. Yet most of the time we do not stop to think about what it truly island. The sun rises, light spills across the horizon, warmth spreads through the air, and life resumes its endless pattern. To us it feels eternal, the golden center of our days and seasons, a steady companion that never falters. But the sun is not just a familiar face in the sky. It is a star, a glowing sphere of plasma, burning quietly in the middle of its long life. And like every other star, it has a past, a present, and a future written into the fire at its core. Our sun is what astronomers call a G-type main sequence star, often shortened to a yellow dwarf. The term dwarf might sound humble, but in reality, the sun is anything but small. It contains more than 99% of the mass of the entire solar system, its gravity anchoring every planet, moon, comet, and asteroid into orbit. At nearly 1.4 million kilometers across, more than 100 Earths could fit side by side within its diameter. Every second, it converts over 4 million tons of hydrogen into helium, releasing energy that streams outward as light and heat. That light takes just over 8 minutes to travel across the empty space to reach our eyes, a reminder that even the nearest star is not quite here, but slightly in the past. Compared to the vast variety of stars in the galaxy, the sun sits in the middle ground. It is neither the smallest nor the largest, neither the faintest nor the brightest. Blue supergiants like Rigel outshine it by tens of thousands of times, while red dwarfs glow so dimly that they would be invisible to us if placed in our night sky. And yet, its middle status is precisely what makes it extraordinary. The sun is steady. It is stable. It shines at just the right brightness, for just the right length of time, in just the right way, to make Earth a place where oceans can remain liquid, plants can thrive, and life can evolve. Its ordinariness is what allowed our extraordinariness. The sun's life, like that of all stars, is measured not in days or years, but in billions of years. Already, it has burned for about 4.6 billion, and astronomers estimate it is just under halfway through its main sequence stage. That means we still have around 5 billion more years before it begins to shift into the next chapter of its story. For now, it balances gravity's pull inward with the outward pressure of nuclear fusion in its core. This balance, delicate yet resilient, allows it to remain stable across vast spans of time. It is the cosmic equivalent of a long, calm breath. Though we take its warmth for granted, the sun is astonishingly powerful. Its surface burns at nearly 60 degrees Celsius, while the core reaches 15 million. Streams of charged particles fly outward in the solar wind, brushing past planets and shaping magnetic fields, sometimes creating auroras when they collide with Earth's atmosphere. Solar flares and coronal mass ejections hurl bursts of energy across the solar system, reminders that even this steady star has tempests hidden within it. And yet, those same outbursts have never threatened to undo the larger balance, the slow and enduring shine that feeds every leaf, every crop, and every breath of oxygen we take. Without the sun, Earth would be an ice-bound rock, adrift in darkness. Its heat powers the circulation of the oceans and the shifting of winds. Its light fuels photosynthesis, which in turn supports the entire chain of life. Even our very bodies carry its legacy. The atoms forged in stars long ago now find themselves warmed by a new star, our star, the one that has guided Earth through countless cycles of growth and change. It is the quiet engine behind every moment of your life, present in every sunrise, every shadow, every glint of light on water. When we look at it compared to the stars scattered across the galaxy, the sun does not stand out in brilliance. It is not among the most massive, nor does it blaze with a searing blue glow. But from our perspective, it is everything. The sun is proof that being average in the grand cosmic scale can still mean being utterly essential. To astronomers studying stars, the sun is a baseline, a standard candle, a reference point by which others are measured. To life on Earth, it is far more than that. It is the hearth around which everything gathers, the center that gives us meaning, direction, and possibility. Its future, though, is written. In billions of years, when the hydrogen in its core is exhausted, the sun will swell into a red giant. Its outer layers will expand, possibly engulfing Mercury and Venus, perhaps even Earth. Its color will redden, its surface will cool, and it will shine with a vastness both beautiful and deadly. After shedding those outer layers, it will shrink down to a white dwarf, a dense ember glowing quietly for eons. That fate is not one we will see, but it is part of its natural arc. Even the most familiar star has an ending. For now, though, we live in its gentle middle age, the sweet spot where stability reigns. Each day, the sun rises and sets, marking time not just for our calendars but for our entire existence. Its light travels across the vacuum of space to warm seas, to glint off leaves, to stir clouds, and to glimmer in the eyes of those who look toward the horizon. Its reliability is its gift, and it is in that reliability that wonder takes root. When you lift your head and feel the sun's warmth, you are not simply feeling heat. You are experiencing the quiet outpouring of nuclear fusion, the same process that powers the most distant stars in the night sky. You are bathed in the light of a star that is both ordinary in the galaxy and extraordinary to us. And though the universe holds billions of stars greater and smaller, brighter and dimmer, it is this one, our sun, that makes life possible here and now. The sun is our familiar star, but in its heart it carries the same mysteries and power as every other. It is a reminder that we are connected to the wider cosmos, not just by imagination, but by energy itself. Every sunrise is a message sent across space, 8 minutes old by the time it reaches us, carrying the warmth that sustains us. To live on Earth is to orbit a star, to depend on it, to belong to it. And in that belonging, we are part of something vast, something that stretches far beyond our small world into the endless night, lit by countless stars like our own. From the moment a star ignites, it begins a long and delicate performance, one that can last millions, billions, or even trillions of years depending on its size. This performance is called the main sequence, the long chapter in a star's life when it quietly fuses hydrogen into helium and shines with a steady light. For us on Earth, it is easy to think of stars as eternal and unchanging and glittering dots that look the same every night. Yet what we see is only a single frame in a story stretched across cosmic time. Stars are not permanent. They shine because deep in their hearts, matter is transformed into energy, and as long as that process continues, they remain alive. At the core of every star lies a furnace, not of fire but of fusion. Hydrogen, the simplest and most abundant element in the universe, is forced together under immense pressure and temperature. At around 15 million degrees in the sun's center, protons are pushed so close that they merge, creating helium nuclei and releasing energy in the form of light and heat. This process is astonishingly efficient. A small fraction of the mass of hydrogen disappears, transformed into pure energy as described by Einstein's famous equation, E mx squared. Even though the fraction is tiny, the mass involved is enormous. In our sun alone, millions of tons of matter are converted into energy every single second, producing the light that sustains life on Earth and streams outward across the solar system. The miracle of stars is not just that they burn, but that they burn with balance. Gravity, the relentless inward pull, is always trying to crush the star tighter and tighter. Fusion, on the other hand, pushes outward with the energy it releases. For most of a star's life, these two forces reach a perfect equilibrium. Gravity presses in, fusion pushes back, and the star remains stable. This balance is so precise that if the fusion rate changes even slightly, the star adjusts itself. If fusion slows, gravity squeezes harder, raising the temperature until fusion speeds up again. If fusion races ahead, the star expands and cools, slowing the process down. In this way, stars act like cosmic thermostats, keeping themselves steady for ages. The main sequence is where stars spend the majority of their lives. How long they stay there depends on their mass. Massive stars burn through their hydrogen quickly, like a bonfire devouring wood, and may last only a few million years before they exhaust their fuel. Smaller stars, however, burn their hydrogen slowly and carefully. Red dwarfs, the most common stars in the galaxy, sip at their fuel so sparingly that they can shine for hundreds of billions, even trillions of years, far longer than the current age of the universe itself. Our sun sits comfortably in between, expected to remain on the main sequence for about 10 billion years in total. It is a cosmic, middle-aged star, stable and steady, with plenty of life still ahead. The energy released during fusion is staggering, far beyond human comprehension. The sun radiates about 400 trillion watts of power, more than the combined output of every civilization that could ever exist on Earth. Yet from 150 million kilometers away, that energy is spread so thin that it feels to us like the warmth of a summer day, soft and gentle. Stars further away may burn even more furiously, but distance dims their gifts. The light we see when we gaze upward is only the faintest echo of what pours from their cores. During their main sequence lives, stars do not remain completely unchanged. Slowly, as hydrogen is fused into helium, the balance shifts. The core becomes richer in helium, and the fusion shell pushes outward. For a star like our sun, this means it gradually brightens over time. Billions of years ago, the sun shone with only about 70% of its current brightness, and billions of years into the future, it will shine more fiercely still. This steady increase is subtle on the scale of human lives, but monumental on the scale of planetary climates and cosmic history. What makes stars so mesmerizing is that despite their unimaginable power, their lives are governed by the same simple laws everywhere. Whether it is a faint red dwarf, glowing dimly in a quiet corner of the galaxy, or a brilliant blue giant lighting up a stellar nursery, the same dance of gravity and fusion dictates their behavior. Their balance is both fragile and enduring, a cosmic conversation between collapse and release, weight and fire. As long as fusion continues, the star remains steady, a beacon of light across the darkness of space. The main sequence, then, is the long heartbeat of a star's life. It is the part we are most familiar with, because nearly every star we see twinkling above us belongs to this stage. The light of Orion's belt, the glow of Sirius, the steady shimmer of Proxima Centauri, all of these are main sequence stars, alive in the same delicate balance as our Sunday. They shine across time, carrying with them the story of matter turning into light, of gravity and pressure, locked in a quiet, ceaseless struggle. When you look at a star, you are seeing not just a point of light, but an ongoing process, a steady transformation that has been happening for millions or billions of years and will continue long after our lifetimes. The light that leaves its surface tonight may not arrive here for decades or centuries, depending on its distance. But when it does, it carries the quiet testimony of fusion, the heartbeat of a star that has been shining across time. Stars endure because they have mastered balance. They last because their burning is not reckless but measured, not chaotic but self-correcting. In that steadiness lies the secret to their longevity, a secret that has given us our sun, our seasons, our days, and our nights. To live in a universe with stars is to live in a universe lit by equilibrium, by the slow and patient release of energy that has defined cosmic history. And as you rest beneath their light, you share in their story, carried along in the calm, radiant glow of stars that have been shining for billions of years and will continue to shine long after you close your eyes. Every star carries within it the certainty of an ending. Just as they are born from clouds of dust and gas, so too must they return what they've borrowed back to the galaxy. The way a star dies depends on how much mass it was given at birth. But whether their finales are quiet or violent, delicate or catastrophic, each one leaves behind not only remnants, but gifts. For the death of a star is never the end of the story. It is the beginning of something else. For stars like our sun, the ending is measured, gentle in its way. After billions of years on the main sequence, fusing hydrogen into helium, the fuel in the core finally runs low. Gravity, patient as ever, presses inward, and the star responds by igniting new layers of fusion in shells around the core. The outer layers swell outward, and the once stable star becomes a red giant, its size ballooning until it dwarfs its original self. One day, the sun will expand so much that it will engulf Mercury and Venus, perhaps even reaching Earth's orbit. Yet from the outside, it will glow softly, red and enormous, a swollen lantern nearing the end of its fire. When a red giant can no longer fuse heavier elements, its outer layers drift away into space, forming a luminous shell of gas called a planetary nebula. Despite the name, this has nothing to do with planets. Early astronomers only thought these glowing clouds resembled planetary disks through their telescopes. The nebula is a final exhale, a fragile bubble of color and light cast into the night. At the center, what remains of the star shrinks down into a white dwarf, a core made mostly of carbon and oxygen, packed into a sphere no larger than Earth. Though it no longer fuses, it still glows faintly with residual heat, cooling ever so slowly over trillions of years. White dwarfs are among the strangest objects in the cosmos. Imagine the mass of a star, like the sun, crushed into a body the size of our planet, where a teaspoon of its matter could weigh as much as a car. The matter is held up not by fusion anymore, but by the quantum pressure of electrons packed tightly together. They are stellar embers, the quiet remains of stars that once blazed. Over time, they will fade to black dwarfs, invisible remnants, but the universe is not yet old enough for any to exist. For now, the cosmos is filled with their dim, ghost-like glow, silent witnesses to stellar lives long gone. But not every star goes quietly. The most massive ones meet their deaths in explosions so violent that they momentarily outshine entire galaxies. When these titans exhaust their fuel, their cores collapse in an instant. Gravity overwhelms everything, crushing the center down to unimaginable densities. The outer layers, no longer supported, rebound outward in a cataclysmic blast, a supernova. These are the grand finales of stellar lives, fireworks on a cosmic scale. For a few weeks or months, a single dying star can blaze brighter than billions of others combined. A supernova is more than destruction. It is creation, In those final seconds, the star forges heavy elements that never existed before: iron, nickel, gold, uranium metals, too heavy to be produced during the calm fusion of a main sequence star. The explosion scatters these elements into the galaxy, seeding clouds that will one day form new stars, new planets, and perhaps even new life. Every atom of iron in your blood was born in such a blast. Every bit of calcium in your bones, every trace of gold in a wedding ring, all of it forged in stellar death throes. Stars die, and in their death, they make us possible. What remains after such an explosion depends on the star's size. For those a few times more massive than the Sun, the collapsed core becomes a neutron star. These are so dense that protons and electrons are crushed together into neutrons, leaving behind an object barely 20 kilometers wide but more massive than the Sun itself. A spoonful of neutron star material would weigh billions of tons. Their surfaces are harder than diamond, their magnetic fields unimaginably strong. Some spin rapidly, beaming radiation like cosmic lighthouses. These pulsars tick across the galaxy, steady as clocks, whispering the rhythm of collapsed stars. For the most massive stars of all, even neutron pressure cannot hold back gravity. The collapse continues until the core shrinks past the point of no return, forming a black hole. Here, gravity is so intense that nothing, not even light, can escape. Black holes are not cosmic vacuums sucking everything in, but silent wells of space-time, invisible except for the effects they have on nearby stars and gas. They are the ultimate end, where matter and energy vanish beyond an event horizon, hidden from view. And yet even these dark hearts have a role to play. They stir galaxies, fuel quasars, and shape the structures of the universe itself. The deaths of stars are not endings in the way we think of death on Earth. They are transformations. The gas blown off by red giants enriches the interstellar medium. The debris of supernova becomes the raw material for new stars and worlds. Even black holes, though they seem like finalities, may influence star formation by stirring gas and feeding energy back into their galaxies. Nothing in the universe is wasted. The cycle continues, one generation giving rise to the next, a chain of creation and destruction stretching back to the first stars that ever shone. When you look at the night sky, it is tempting to see permanence, a timeless sea of light. But hidden in those points are stories of beginnings and endings, of lives already gone and others just starting. Some of the stars above you tonight may already have died, their light only now reaching us across the gulf of years. Others are still young, burning steadily, and someday their deaths will give birth to new wonders, yet unseen. The strange deaths of stars remind us that in the universe, endings are beginnings. A planetary nebula may look like a fading sigh, but it is also the birth cloud for new chemistry. A supernova may look like destruction, but it is also the forge of worlds. A neutron star may seem like an inert husk, but it blazes with energy that travels across galaxies. Even a black hole, silent and dark, is part of the cosmic balance, shaping the space around it. Everything we know and everything we are comes from stars that lived and died long before the sun was born. To rest under the stars is to rest under a history of countless endings and countless renewals. In their strange deaths, stars leave behind not silence, but possibility. And though their light may dim, their gifts endure, scattered across time, waiting to be gathered once more into life. In the quiet night sky, stars seem eternal, steady, and calm. Yet behind that stillness lies a menagerie of objects so strange and so extreme that they defy our everyday sense of what a star can be. Some are remnants of explosions, spinning faster than a kitchen blender, sending beams of energy across space like cosmic lighthouses. Some are wrapped in magnetic fields so powerful they could erase data from hard drives on Earth from halfway across the galaxy. Others are hurled at unimaginable speeds, flung from the Milky Way itself, cast into the darkness between galaxies. These are the exotic stars, the outliers, the rare ones, the stars that remind us the universe has a taste for the extraordinary. Among the strangest are pulsars. Born in the chaos of a supernova, a pulsar is the compressed core of a once massive star, now a neutron star only about 20 kilometers wide, but more massive than our Sunday. When these remnants spin, and some spin incredibly fast, beams of radiation pour from their poles. If the beam happens to sweep past Earth, we see it as a pulse of light, rhythmic and steady, flashing dozens or even hundreds of times every second. These pulses are so regular that astronomers compare them to clocks, measuring their precision down to microseconds. Imagine a collapsed star, smaller than a city, spinning 30 times a second, its magnetic fields tearing space around it, its radiation sweeping out like the hand of a clock ticking across the cosmos. That is a pulsar, and they are real. Even stranger are magnetars, a rare type of neutron star with magnetic fields 1,000 times stronger than those of ordinary pulsars. To say these fields are powerful is to undersell the word itself. A magnetar's magnetic force is billions of times stronger than anything humanity can create. If one were as close as the moon, it could disrupt the structure of atoms in your body. Most are quiet, but occasionally they release bursts of energy so intense they can outshine all the stars in the Milky Way for a fraction of a second. These outbursts ripple across space as gamma rays, detectable from halfway across the galaxy. To imagine something so small, so dense, and so violent is to realize that nature's imagination is far wilder than ours. Not all exotic stars are born in solitude. Some exist in pairs, locked in binary systems, orbiting one another in intimate gravitational embrace. These partnerships can become dramatic when one star evolves faster than the other. A white dwarf may siphon gas from its larger companion, stealing material until it grows unstable and erupts in a nova. A neutron star may tear matter from its partner, heating it until it glows brightly in X-rays. And in the most extreme cases, two neutron stars or black holes may spiral together, colliding in an event so violent it shakes the fabric of space-time itself, releasing gravitational waves that ripple across the universe. What looks like a single point of light in the sky may, in truth, be two stars dancing in a deadly embrace. Some stars are not bound at all. Hypervelocity stars are flung through the galaxy at speeds so high they can escape its gravity entirely. Imagine a star racing away at over 1,000,000 kilometers per hour, fast enough to leave behind the spiral arms and travel alone into intergalactic night. These stars are rare, but they exist, and many are thought to be survivors of close encounters with black holes. In some scenarios, a binary system wanders too near the supermassive black hole at the center of the Milky Way. One star is captured, swallowed by the black hole's pull, while the other is hurled outward like a slingshot, racing away forever. These runaway stars are exiles, glowing pilgrims set adrift beyond the borders of galaxies. The catalog of exotic stars does not end there. Some stars flare with such ferocity that their brightness can increase 1,000-fold in mere minutes, then fade again just as quickly. Others are carbon stars, whose atmospheres are rich with soot-like molecules that give them deep red hues, glowing like embers smoldering in the dark. There are Wolf-Rayet stars, massive and unstable, blasting off their outer layers in powerful stellar winds that strip them down to their cores. These stars shine fiercely, their lifespans measured not in billions of years like the sun's, but in mere millions. They live hard and die young, leaving behind supernovae and black holes. What makes these rare stars so captivating is not just their strangeness, but the way they reveal the extremes of physics. Pulsars and magnetars show us the limits of density, magnetism, and rotation. Binary systems reveal how gravity can bind stars into relationships that reshape their lives and deaths. Hypervelocity stars remind us that even the most massive objects in the galaxy can act like slingshots, flinging suns into the void. And all of them, in their way, enrich the galaxy, scattering material, stirring energy, and writing new chapters in the story of creation and destruction. If you look at the night sky with the naked eye, you see serenity. But hidden within that serenity are stars spinning at incredible speeds, stars whose surfaces seethe with winds faster than hurricanes, stars wrapped in magnetic coils so strong they warp reality itself. Some stars are steady companions, like our Sunday, but others are restless, violent, fleeting, or wandering. They are reminders that the universe is not only vast, but endlessly varied. It is tempting to think of stars as uniform, just points of light scattered in darkness. Yet some of those points are pulsars ticking their way through time. Some are magnetars waiting for their next violent outburst. Some are exiles racing away faster than the galaxy can hold. When you realize this, the stars stop being distant and abstract. They become characters, each with their own story, each shaped by the same forces of gravity, fusion, and time, but driven to different fates. The universe does not repeat itself endlessly. It experiments. It creates ordinary suns like ours, yes, but it also forges these rare, strange wonders. Stars that are clocks, stars that are magnets, stars that are bullets shot across intergalactic space. And each one, no matter how unusual, fits into the larger fabric of the cosmos, woven into its rhythm of creation, destruction, and renewal. Even the strangest stars are not mistakes. They are the universe's way of reminding us that reality is wider, stranger, and more beautiful than we have yet imagined. When you look up at the stars, they appear fixed, as if someone pinned them to the sky in patterns that never change. Constellations seem eternal, Orion rising in winter, Scorpius curling through summer. But this stillness is an illusion born of distance. Stars are not nailed in place. They are moving, every single one of them, following vast orbits that curve around the center of the galaxy. Our sun is one of them, sweeping in a long, slow arc that takes hundreds of millions of years to complete. To our eyes, the heavens seem quiet, but in truth, the night sky is alive with motion, a grand procession that we cannot see in a single lifetime. Each star belongs to the Milky Way's gravitational dance. At the heart of our galaxy lies an immense concentration of mass, stars, and gas, and a supermassive black hole. And around this invisible anchor, the stars orbit like sparks around a fire. Some move close to the center, circling quickly, their paths compressed into a few million years. Others drift in the halo, taking billions of years to complete just one journey. Our solar system, modest and ordinary, is about 2/3 of the way out from the center, orbiting at over 800 kilometers per hour. And yet, despite that astonishing speed, we cannot feel it. Our orbit is so vast that even after the entire history of human civilization, we have barely advanced along a fraction of our galactic path. If you could compress time, speeding up millions of years into minutes, the stars would no longer appear static. They would swirl like a slow tide, constellations breaking apart and reforming into unfamiliar shapes. The Big Dipper's ladle would stretch until it bent beyond recognition. Orion's belt would unravel. The sky of the far future will not be the same sky we know now, because the stars themselves are travelers, each carrying its own trajectory through the galaxy. Astronomers measure this hidden motion with precision, and what they find is both subtle and dramatic. The term is proper motion, the slow shift of stars across the sky, measured against the background of more distant objects. Most stars creep along at such a glacial pace that their positions barely change over centuries. But some are restless, sliding quickly across the heavens from our point of view. The fastest of them all is Barnard's star, a small red dwarf only 6 light-years away. Though dim and invisible to the naked eye, its motion is remarkable. Every human lifetime it shifts noticeably, racing across our sky faster than any other star known. It reminds us that even the most unassuming stars can reveal the ceaseless movement of the cosmos. But the stars are not only sliding side to side across our vision, they are also drawing nearer or receding, their light stretched or compressed as they move relative to us. Some are rushing toward the sun, others are drifting away. When mapped in full 3 dimensions, their paths weave into a web of motion, converging, diverging, and sometimes crossing. In the crowded heart of the galaxy, stars occasionally pass dangerously close, tugging at one another with gravity, disturbing orbits, and scattering planetary systems. In the densest regions, within globular clusters or near the core, stars can even collide. These rare encounters release brilliant flashes of light, fusing 2 suns into one, or producing exotic remnants that shine with strange intensity. There are stars that do not stay bound at all. Some are ejected from the galaxy entirely, victims of gravitational slingshots. When binary stars pass too close to the supermassive black hole at the Milky Way's center, one may be captured, swallowed by the black hole's pull, while the other is hurled outward at speeds great enough to escape the galaxy itself. These hypervelocity stars are outliers, lonely exiles traveling into intergalactic space. Imagine a star, perhaps with its planets still circling, cast adrift into the vast emptiness beyond the Milky Way, destined to shine in isolation for billions of years, carrying with it the memory of the galaxy it once called home. Even stars that remain bound do not orbit in simple circles. Their paths are often stretched into ellipses, tilted above and below the galactic plane, or warped by encounters with other masses. The sun itself does not travel in a perfectly flat loop. Instead, it bobs gently up and down through the galaxy's disk, rising and falling like a cork on a slow wave. Every few million years, it passes above the plane before sinking back down again. These vertical oscillations are invisible to us on human timescales, but they remind us that the galaxy is not a rigid system. It is flexible, dynamic, filled with rhythms we can only glimpse through patient measurement. And while the stars are in motion, so too is everything else. Clouds of gas drift along their own paths, stretched into tendrils by gravity. Stellar streams, long ribbons of stars torn from dwarf galaxies, wrap around the Milky Way like scarves of light, tracing the memory of collisions long past. Clusters of stars are slowly unraveled, their members scattering one by one into the wider galaxy, their family ties loosened by tidal forces. Nothing in the sky is fixed. All is moving, shifting, transforming. To lie beneath the stars is to see only a frozen moment of their journey. But in truth, you are watching a vast system in motion, 100 billion suns circling a common center, each one tugged and guided by the unseen hand of gravity. Some are racing ahead, some are falling behind, some are straying far from the disk, and some are rushing toward endings we cannot yet see. Our own star, steady and bright, is simply one traveler among them, orbiting in its long loop, carrying Earth along like a passenger on a ship adrift in the galactic sea. The stars we see tonight are not eternal fixtures. They are fellow wanderers, and as they drift, collide, or are flung into the dark, they weave together the changing shape of the galaxy itself, a story written not in words but in motion, patient and unending. On a clear night, far from the wash of city lights, certain stars command your attention at once. They gleam with a sharpness that seems almost alive, as if they are closer to us than the rest, as if they alone are reaching out across the dark. For as long as humans have gazed upward, these brightest stars have been our companions, woven into stories, marked as guides, and remembered as more than points of light. Yet their brilliance is not always what it seems. Some are dazzling because they truly burn with immense power, radiating more energy than our sun could dream of. Others only appear bright because they are close neighbors, their modest fires magnified by proximity. The night sky, for all its clarity, carries illusions, and the stars remind us that perception is not always reality. The most famous of these beacons is Sirius, the dog star, gleaming white in the constellation Canis Major. To the eye, it is unmistakable, brighter than all other stars, almost seeming to flicker with rainbow hues when seen near the horizon. For ancient civilizations, Sirius held enormous importance. Egyptians tied its rising to the flooding of the Nile, a rhythm on which agriculture and survival depended. To sailors, it was a marker of direction across vast oceans. And today, it still shines as the brightest point in Earth's night sky. Yet Sirius is not extraordinary in its power. It owes much of its brilliance to its closeness, lying just over 8 light-years away, practically a neighbor in cosmic terms. Its light dominates not because it is the strongest, but because it is one of the nearest. Then there is Vega, a jewel in the small constellation Lyra. It shines with a crisp, bluish-white intensity, one of the easiest stars to spot during the summer months of the Northern Hemisphere. Vega is both genuinely luminous and relatively close, only about 25 light-years away. Once, 12,000 years ago, it was the pole star, the anchor of the northern sky, and it will be again in another 12, 0 years as Earth's axis slowly wobbles. For now, it glitters high above like a steady lantern, an object so bright that astronomers once used it as a standard for measuring the brightness of all other stars. To look at Vega is to see not only a beacon of the present, but also a reminder of how Earth itself shifts and changes beneath the stars. Some of the brightest stars capture us not with steadiness, but with drama. Betelgeuse, the red shoulder of Orion, glows with a warm, ruddy hue, a stark contrast against the blue-white stars around it. It is a red supergiant, massive and unstable, nearing the end of its life. Its surface swells and contracts, causing its brightness to vary over months and years. Recently, it dimmed so noticeably that skywatchers wondered if it was about to explode as a supernova, though it recovered in time, its light growing strong again. Still, that dimming was a reminder that stars are not eternal fixtures. Even the brightest can falter. One day, Betelgeuse will collapse and erupt in one of the most dramatic events the galaxy can offer. When it does, it may outshine the full moon, a sudden beacon brighter than all others, visible even in the daytime. For now, it smolders quietly, a giant in its twilight, a living reminder that brilliance can be fragile. Rigel, Orion's foot, offers another kind of power. It shines blue-white, one of the most luminous stars visible from Earth, radiating tens of thousands of times the energy of the sunday. Though it lies over 800 light-years away, it is still one of the brightest points in our sky. Its distance hides the true scale of its might. If Rigel were placed where the sun now stands, its light would be so intense that Earth's surface would be scorched and uninhabitable. The fact that it appears alongside Betelgeuse in the same constellation is a cosmic irony. One, a dying red giant. One, a hot, massive young star, both captivating in different ways. Orion's outline has drawn human eyes for millennia, and much of that is owed to the twin beacons of Rigel and Betelgeuse. What makes these stars stand out is not only their physical power, but also their relationship to us. Brightness, after all, is not a simple measure. There is intrinsic brightness, the true amount of energy a star emits, and there is apparent brightness, the intensity as it reaches us across space. A small, ordinary star nearby can appear more striking than a colossal star thousands of light-years away. Our eyes are limited instruments, fooled by distance, dazzled by proximity. To us, Sirius seems greater than Rigel, though in reality Rigel is far more luminous. The night sky is a mirror of perspective, and the stars that stand out are the ones closest to our particular place in the universe. And yet, because of that perspective, These bright stars have shaped the way we think. Constellations are anchored by them, stories are woven around them, and navigation has depended on their steadiness. For most of human history, the brightest stars were the most trustworthy companions. Their predictability in rising and setting gave rhythm to calendars, guided migrations, and became symbols of gods and myths. Sirius, Vega, Betelgeuse, Rigel. These stars are more than astronomical facts. They are cultural touchstones, written into the language of humanity as enduring markers of the sky. To lie under these bright beacons is to feel both clarity and humility. Clarity, because their brilliance cuts through the dark, unwavering and vivid, offering a sense of direction in the vast night. Humility, because when we learn what they really are, some close, some distant, some young, some dying, we realize that their appearance is not always their truth. The brightest star may be ordinary. The dimmest speck may be a giant, hidden by sheer distance. The contrast between perception and reality is part of their poetry, a reminder that the universe is larger, more complex, and more deceptive than our eyes alone can tell. And so the brightest stars remain our gateways. They are the first lights children notice when they look up, the fixed points that artists paint and poets describe, the guides that travelers once relied upon across seas and deserts. They shine not only with energy, but with meaning, carrying the weight of history and imagination, as well as science. To see them is to glimpse both the truth of physics and the truth of perception, blended together in the most familiar symbols of the night sky. And even as new generations look upward, their glow remains the same. Ancient fires burning steadily across time, lighting the way through darkness. When we imagine the sky, we often picture it like our own solar system, with one star at the center holding its planets in place. The sun feels like the natural arrangement, a solitary anchor surrounded by worlds. But in truth, our star is an exception. Across the galaxy, most stars do not live alone. They are born and remain bound together in pairs, trios, or even larger families, their gravity tying them into intimate partnerships that can last for billions of years. Instead of one steady beacon, most suns rise and set with companions, orbiting each other in patterns that are as graceful as they are complex. Our sun may be solitary, but it is surrounded by a universe of dancers. A binary star system begins with two stars bound by gravity. Sometimes they are born together, collapsing from the same cloud of gas and igniting in tandem, like siblings that never part ways. Other times, stars capture one another through slow gravitational encounters, caught in each other's pull until their fates are entwined. Once paired, they move in an endless dance, circling a common center of mass, a point invisible in space, but real in its influence. To an observer, it may look like one star loops around the other, but in truth, both are moving, both are curving, held in balance by their shared pull. This is the most common arrangement in the Milky Way. For every solitary sun like ours, there are two or more locked in cosmic embrace. Some binaries are wide and leisurely, separated by vast distances so that their motion is slow and stately, taking thousands of years to complete a single orbit. Others are tight, so close that they may circle one another in just days or even hours. In these close systems, the stars feel each other's presence intensely. Their surfaces may bulge toward one another, stretched by tides of gravity. Streams of matter can spill across the gap, falling from one star to the other in glowing arcs of gas. In the most extreme cases, they share a common envelope, two stellar cores wrapped inside one swollen shroud, orbiting within the same body of gas until they merge or are torn apart. These are not gentle partnerships, but fiery ones, where gravity pulls not just on orbits, but on the very flesh of the stars themselves. Triple star systems and higher multiples add another layer of elegance. Imagine three suns, not aligned in some neat triangle, but moving in a hierarchy of orbits. Two might circle each other closely, while the third loops much farther out, completing a slow, distant path. Sometimes the arrangement is reversed, with a central star orbited by two companions moving in tandem. The mathematics of these motions is intricate, and yet the stars hold their rhythm, repeating their paths across ages. To a planet caught in such a system, the skies would shift in ways almost unimaginable to us, two dawns rising together, or one star following another into the night, or even three suns stretching shadows in strange directions across a world's surface. There are binaries so close they eclipse each other from our point of view, taking turns passing in front and dimming the combined light we see from Earth. These eclipsing binaries, though tiny points of light in the sky, tell astronomers everything about their sizes, masses, and even the shape of their orbits. In their flickering, predictable rhythm, they reveal secrets that a single star could never disclose. Others pulse not with eclipses, but with violence, as material ripped from one star swirls onto the other, forming bright accretion disks that glow fiercely in X-rays. These systems are both destructive and creative, reshaping the fates of the stars involved, turning companionship into a crucible. What makes these stellar pairs and trios so remarkable is not just their abundance, but the poetry of their motion. To watch them in simulation, or in the mind's eye, is to see a waltz carried out in silence, graceful arcs traced over and over, sometimes for billions of years. The balance is delicate, but enduring. The partners may never touch, may never change their distance, yet they remain bound, orbiting endlessly as if the galaxy itself had set the music and they simply could not stop moving to it. And sometimes these dances end dramatically. A massive star in a binary may explode in a supernova, blasting its companion with energy and ejecta, stripping atmospheres, or even altering orbits. In some cases, the surviving star is flung free, sent speeding across the galaxy as a runaway, carrying with it the memory of the partner it lost. Other times, the explosion leaves behind a dense remnant, perhaps a neutron star or black hole that continues the orbit, an unseen but powerful partner. A living star circling a collapsed corpse is one of the strangest and most haunting images in astronomy. One light still shining, one gone dark, yet both forever linked. It is almost certain that our sun was once not alone. Clues in the motions and chemistry of nearby stars suggest that it was born in a cluster, a nursery where dozens, perhaps hundreds of suns ignited together. Some of them may have formed binaries and triples that still circle each other today. Our sun drifted apart from its siblings, breaking free into solitude, and perhaps it lost a companion of its own, a twin that may still wander somewhere in the galaxy. If true, that twin would be unimaginably distant now, just another star among billions. Our solitary existence may simply be the result of separation, a dance partner lost in the crowd. To think of the galaxy this way is to imagine it not as a scatter of isolated lights, but as a ballroom of movements, a vast gathering where stars swirl together in countless combinations. Some steps are slow, some are hurried, some are violent, and some are tender. Most are not alone, but partnered, their paths curved and intertwined in ways we can only measure from afar. And even from that distance, the beauty of their waltz is unmistakable. Above us, what looks like stillness is in truth motion. The stars we see as steady points are orbiting one another, circling unseen centers, tracing loops that will continue long after we are gone. They are not frozen in the night sky. They are dancing, ceaselessly, tirelessly, to music older than life itself. For as long as humans have lifted their eyes to the night sky, the stars have been more than distant lights. They have been guides, storytellers, calendars, and companions. Long before telescopes revealed their true nature as suns scattered across a galaxy, they were woven into myths and legends, shaping how entire civilizations understood their place in the universe. To sit under the night sky, thousands of years ago, was not to look into an anonymous void, but into a tapestry alive with gods, animals, heroes, and omens. The stars were the original text written across the heavens, and every culture found meaning in the way they burned. The ancient Egyptians aligned their lives with the stars. The appearance of Sirius in the pre-dawn sky, just before the annual flooding of the Nile, was more than a celestial event. It was a signal of survival, a marker that told them when the river would rise and bring life-giving water to the fields. They watched it faithfully, linking it to the goddess Isis, who wept for her lost husband Osiris, her tears said to swell the Nile. This single star connected myth to sustenance, divinity to the rhythms of agriculture. The heavens above were not separate from the earth below, but an extension of it, reflecting and guiding the cycles of life. In Greece, the sky was a canvas for stories of heroes and monsters. Orion, the great hunter, was placed among the stars after his death, still striding across the heavens with his belt and sword. Perseus holds the head of Medusa forever in his grasp, while Andromeda lies chained to the rocks of the sky. To the Greeks, constellations were more than shapes. They were myths preserved in light, eternal retellings of their most enduring tales. Even today, we still use their names, still recognize their patterns, unknowingly tracing the myths of an ancient people every time we glance upward. For the Polynesian navigators, stars were maps. Without compasses or written charts, they crossed the vast Pacific Ocean by memorizing the rising and setting of hundreds of stars, knowing which ones marked the direction to distant islands. They read the night sky as one might read a familiar trail, noting how constellations shifted through the seasons, and how pairs of stars marked the celestial highway across open waters. Their canoes sailed thousands of miles guided only by starlight, a testament to how deeply the human mind can bond with the sky when it must. For them, stars were not distant mysteries but practical companions, leading them safely from horizon to horizon. The Maya and other Mesoamerican civilizations built temples aligned with the stars and planets. They tracked Venus with extraordinary precision, treating its cycles as divine. Venus was the morning star, the harbinger of change, tied to warfare and ritual. The stars gave them not just calendars for planting and harvest, but sacred rhythms for sacrifice and ceremony. Their myths did not separate the heavens from fate. The two were entwined, as if the gods themselves were etched in light overhead. The cosmos was not abstract but immediate, its influence felt in every season, every ritual, every breath. In northern cultures, the stars kept travelers alive during long winters. The Big Dipper pointed to Polaris, the North Star, a fixed beacon in a sky of wandering lights. To Vikings and other seafarers, it was an anchor of direction, a trustworthy guide when waves and storms obscured all else. Its place at the celestial pole made it appear steadfast, unmoving, a symbol of constancy. Even today, Polaris holds that role, quietly marking the North in a way so simple and reliable that countless generations have placed their trust in it. In India, the stars became the foundation of astrology, their positions mapped into intricate charts used to divine human fate. The constellations of the zodiac, known across many cultures, became the signs of character and destiny, a link between the motions of heaven and the struggles of life. Though science has since separated astronomy from astrology, the connection shows how deeply the human desire to find meaning in the stars runs. Whether for guidance at sea, predictions of harvest, or revelations of the soul, the stars were always more than objects. They were mirrors of existence. Even in the harsh emptiness of deserts, the stars became rivers. For the peoples of the Sahara and Australia, the Milky Way was imagined as a great flowing waterway, a celestial reflection of life on Earth. Some saw animals crossing it. Others saw spirits traveling along its shining length. The dark patches of dust became emus, serpents, or ancestral beings, shaped not by the light of the stars but by the shadows in between. Where there was little water, the heavens gave one, painted in light, eternal, and dependable. What unites all these myths and uses is the sense that stars were never just distant fires. They were woven into human stories as symbols of hope, warning, guidance, and remembrance. Their regular rising and setting marked the passage of time, their seasonal shifts tied to planting and harvest, migration and ritual. They gave structure to the chaos of existence, offering both mystery and order. Even without telescopes, humans knew that the stars mattered, that their motions carried weight, and their presence was more than decoration. Science has since shown us what stars truly are. Nuclear furnaces burning billions of miles away, governed by physics rather than gods. Yet the wonder remains. When we speak of Orion, we still tell the story of a hunter chasing his prey. When we look for the Pleiades, we still remember them as sisters pursued across the heavens. When we follow Polaris, we still trust it as a guide, just as our ancestors did. The myths linger because they capture something deeper than fact. They capture the way stars feel. The night sky is not empty. It is a library of human memory. Every constellation, every story, every use of a star for timekeeping or navigation is a reminder of how deeply we are tied to them. They are suns, yes, vast and distant, but they are also storytellers. They have whispered to us across generations, teaching us to sail, to plant, to dream, to imagine gods and monsters, to measure our days. In their light, we found both the practical and the poetic, the survival of our bodies and the expansion of our minds. Even now, when satellites crowd the skies and electric light drowns the stars from many cities, the connection endures. A child looking up and tracing a shape in the stars is continuing the same tradition as the first humans who sat by a fire and gave names to the heavens. We may know more of their science, but the myths still live. The stars remain companions of our imagination, reflections of our fears, and symbols of our hopes. They shine above us, steady and silent, carrying both the truth of physics and the stories of humanity. They remind us that knowledge and wonder are not opposites, but two ways of seeing the same eternal lights. Every star in the night sky seems to shine with a simple, steady light. To the naked eye, it is only brightness, a distant flicker against the black. But hidden inside that light is a code, an ancient script written in the language of physics and chemistry. For those who know how to read it, starlight becomes more than a shimmer. It becomes a story. Each ray carries not only the warmth of fusion, but also the whispers of a star's temperature, size, composition, and even its age. The stars cannot speak, but they do not need to. Their light does the talking. When starlight passes through a prism or a finely tuned instrument, it spreads out into a rainbow. Yet this rainbow is not perfect. Dark lines cut across it, as if pieces are missing, stolen away. These are absorption lines, fingerprints left by the atoms within the star. Hydrogen, helium, iron, calcium. Each element leaves its mark, absorbing just the right wavelengths. By examining these tiny gaps, astronomers can reconstruct the ingredients of a star, reading its chemistry as easily as words on a page. Every star carries this unique pattern, and no two are exactly alike. It is through this method, spectroscopy, that we know what stars are made of. The sun, for instance, is mostly hydrogen, with helium and traces of heavier elements. Others are rich in metals, or stripped nearly bare, revealing differences in age and origin. This is how we discovered that stars in the galactic halo are metal poor, relics of a time when the universe was young and heavy elements were rare. Their light does not just tell us about themselves, but about the cosmos, as it was billions of years ago. To look at them is to peer into history, their photons having traveled across space carrying ancient information. Light reveals temperature as well. A star's color is not only a matter of beauty but of physics. Blue stars blaze at tens of thousands of degrees, their photons bursting with high energy, while red stars glow cool and soft, their surfaces barely warm enough to sustain a gentle simmer of fusion. By analyzing where most of a star's light falls along the spectrum, scientists can determine its surface temperature with astonishing precision. A casual glance may mistake one star for another, but through their color, they quietly announce their true heat and character. Distance, too, can be measured in light. The way brightness diminishes with space allows astronomers to judge how far away a star really is. Some stars, called standard candles, have predictable luminosities, and by comparing their known brightness to what we see, we can measure their distances across millions of light years. Without this trick of light, the scale of the universe would remain hidden, collapsed into a flat ceiling overhead. Instead, stars use their glow to reveal the vastness, mapping out space with nothing more than their radiance. Even motion is written into light. When a star drifts away from us, its light stretches, shifting toward the red end of the spectrum. When it moves closer, the light compresses, sliding toward blue. This Doppler effect lets astronomers track the dance of stars, the tug of unseen companions, and the expansion of the universe itself. Whole galaxies are seen fleeing from us through this signature shift. What seems like a steady light is, in truth, a messenger of movement, a record of velocity, folded into the very waves that reach our eyes. Perhaps most haunting is the way starlight functions as a time machine. Light does not travel instantly. It moves at a finite speed, swift beyond imagination, but not infinite. This means that when you look at a star 100 light-years away, you are not seeing it as it is tonight, but as it was 100 years ago. A star 1,000 light-years away is already 1,000 years behind. The further we look, the further back we travel. Some of the stars above us may no longer exist, their deaths long since come, but their light still streams through space, still painting the sky as if nothing has changed. The heavens above are not a mirror of the present, but a layered archive of the past. The chemical fingerprints revealed in starlight show us something even more intimate: our own story. When astronomers studied the spectra of stars, they found that the heavy elements iron, carbon, oxygen, calcium were forged in earlier generations of suns. The iron in your blood, the calcium in your bones, the oxygen you breathe, all carry the marks of stellar forges. By decoding starlight, we discover that we are not separate from the stars but born of them. Their light carries not only their history but our own. To the eye, a star may seem eternal and unchanging, but when its light is stretched apart and studied in detail, it reveals a life in progress. It may show the turbulence of rotation, the flare of sunspots, the gentle swell of pulsations. It may reveal whether a star is young and vibrant, middle-aged and steady, or old and fading. Even the process of death can be traced through spectral lines as elements heavier than iron appear in the ashes of supernova remnants. A star whispers its life story continuously, whether we listen or not, and we do listen. Instruments on Earth and in orbit catch these photons, split them into spectra, and trace their delicate signatures. From them, scientists build models of stellar interiors, maps of galactic evolution, and timelines of cosmic history. But beneath the equations lies something quieter: awe at the way light carries memory. To gaze at a star is to encounter a messenger that has traveled across incomprehensible gulfs of time and space, carrying with it everything the star is willing to tell. Each star is more than a dot in the sky. It is a voice, whispering in wavelengths, sharing its secrets in colors too subtle for the eye alone. To us, they appear silent, scattered, and remote. But in truth, they are speaking constantly, filling the cosmos with messages. And with every spectrum, Every fingerprint revealed, we come closer to understanding that the stars are not just distant suns. They are storytellers of the universe, weaving their tales in light. On a clear night, far from the wash of city lights, the sky opens into a river of glittering points. To the human eye, there might be a few thousand visible stars, each one sharp and luminous, seemingly countless. And yet this is a mere sliver, a faint whisper of the true number that exists. The Milky Way alone is thought to cradle somewhere between 100 and 400 billion stars, each one a sun in its own right, each with its own story of birth, life, and eventual death. What we see is almost nothing compared to what lies beyond, scattered like hidden treasure across the dark. When astronomers speak of the observable universe, the scale grows beyond comprehension. The best estimates suggest there are roughly a septillion stars, that is a 1 followed by 24 zeros, shining within reach of our telescopes. That number is so vast it resists being grasped, slipping through thought like sand through fingers. It means there are more stars than grains of sand on every beach on Earth, more suns burning in silence than words ever spoken by humankind. Each one is a point of light, many too distant for our eyes to ever detect, and yet together they weave the great fabric of the cosmos. The irony is that despite such staggering abundance, we see so little of it. Without tools, the naked eye under the best conditions perceives only a few thousand stars. Their light must be both bright enough and close enough to pierce the veil of our atmosphere. Dust clouds within our galaxy block many more, hiding them behind curtains of darkness. Others are simply too far away, their light stretched thin over unimaginable distances until it dissolves into invisibility. The night sky looks full to us, but it is, in truth, almost empty compared to what is truly there. This limitation, however, is not a flaw but a gift. To be human is to live within a certain scale, where thousands of stars feel immense enough to stir wonder, but not so overwhelming that they crush thought beneath their weight. The visible sky is a window, a portion carefully balanced between mystery and familiarity. We look up and see a manageable sea of lights, each one a reminder of the infinity beyond. If the full number of stars were visible all at once, the heavens might blaze too brightly, leaving no room for darkness, no canvas for imagination. The universe hides most of its suns, perhaps so we may marvel at the few it allows us to see. Even so, the numbers hold power. To imagine hundreds of billions of stars in our galaxy alone is to feel the smallness of our own world. Earth becomes one pebble in a beach without end, our sun only a single ember in a fire that stretches across cosmic time. But this smallness need not frighten, for in being small, we are placed within a context vast and enduring, a reminder that our struggles and fleeting moments are not the whole of existence. The scale itself is soothing, like stepping into a wide landscape and realizing you are part of something larger, timeless, and still unfolding. The fact that stars are so numerous also means variety beyond imagination. Among those hundreds of billions are tiny red dwarfs glowing faintly for trillions of years, massive blue giants burning hot and fast, pairs and triplets bound in delicate orbits, clusters holding thousands together, and solitary wanderers adrift between galaxies. Each star is unique, and yet together they form patterns that repeat across scales, like notes in a cosmic symphony. From our perspective, they appear interchangeable, dots of light scattered without order. But on the scale of billions, they reveal order and rhythm, the architecture of galaxies, the spiral arms, the glowing clusters, the faint halos. And then there is the thought of other suns hosting other worlds. If there are hundreds of billions of stars in our galaxy and septillions across the universe, the probability that many have planets is overwhelming. Already we know that planetary systems are not rare but common, perhaps even the rule rather than the exception. Each star may carry its own retinue of worlds, some barren, some strange, and perhaps some like Earth, cradling life under alien skies. The sheer number of stars becomes not only a fact of scale, but a question of possibility. With so many suns, how many harbors of life must be hidden in the dark? The ancient poets and navigators who looked at the night sky had no way to guess at these numbers. To them, the stars were countless simply because the eye could not tally them. The infinity they felt was a matter of perception. Now we know the scale with far greater accuracy, and the result is not to diminish wonder but to deepen it. The true count of stars is beyond the reach of memory or language, and so it becomes an infinity in its own way, an endlessness the mind can only circle but never hold. In this way, the stars humble us. They remind us that our Earth, our histories, and even our galaxy are small parts of something immeasurably vast, yet they also soothe us, offering a kind of quiet perspective. To know that there are hundreds of billions of stars shining right now within our galaxy and septillions beyond is to know that the cosmos is steady and full. We are not standing in an empty place, but within a universe rich with suns, each one a beacon of endurance across time. And when we look up, seeing only the few thousand permitted to our eyes, we can let the rest remain hidden. The unseen stars are still there, filling the dark with their quiet light, waiting for the right instruments or the right moment to reveal themselves. The night sky may be sparse, but in that sparseness lies its beauty. It is a window into infinity, framed small enough for us to bear, and beyond the window, countless stars burn on, steady as breath, endless as silence. When we look at the night sky, we tend to think of stars as solitary lights, each one standing alone in the vast dark. For centuries, that was how humanity understood them, pinpoints of brightness without companions, or perhaps fixed jewels set into the dome of heaven. Only in recent decades have we begun to understand the fuller truth. Most stars do not shine alone. Around them orbit entire families of worlds. Planets are not rare curiosities but near inevitabilities, born from the very process that gives rise to stars themselves. For every star, there may be several planets, and together they make the universe far more crowded, far more alive with possibility than we ever imagined. Astronomers now suspect that planets actually outnumber stars. That means in our galaxy of hundreds of billions of suns, there may be trillions of planets drifting in orbit, hidden from naked sight but no less real. Some are gas giants larger than Jupiter, blazing hot from the nearness of their parent star. Others are small rocky worlds, baked or frozen, hugging close or wandering far. Many orbit in ways that would seem impossible by our standards, their years lasting only days, or stretched across centuries. The discovery of exoplanets, planets around other stars, has transformed our view of the cosmos. What once seemed unique to our solar system is, in truth, ordinary. We are not an exception. We are the rule. The birth of planets is tied to the birth of stars. When a star ignites in its stellar nursery, it is often surrounded by a swirling disk of gas and dust, remnants of the cloud that collapsed to form it. Within this disk, particles collide and stick, growing into clumps, then into rocky bodies, then into full planets. In this way, planets are children of stars, sculpted from the same material, bound to them by gravity and light. A star is not only a furnace of energy, but an architect, shaping the environment in which worlds can form and evolve. Without stars, planets could not exist, and without planets, life as we know it could not find a home. Some of these planetary systems are stranger than anything dreamed of in ancient stories. There are worlds with double sunsets, circling binary stars that rise and set in pairs. There are planets orbiting pulsars, bathed in lethal radiation, remnants of systems torn apart by supernovae. There are hot Jupiters that skim so close to their stars that their atmospheres boil away into space, and rogue planets, ejected from their systems, drifting alone through the interstellar dark with no sun to warm them. The variety is staggering. each discovery more unexpected than the last, yet each one a reminder that the universe builds on a grand scale, experimenting with every possible configuration. For Earth, the relationship with our star is not just structural but existential. The sun provides not only light and warmth but stability, holding our planet in a balance that allows oceans to remain liquid, air to remain breathable, and life to flourish. Astronomers sometimes speak of the habitable zone, the band around a star where conditions might allow water to exist as a liquid on a planet's surface. Too close, and the heat strips away everything. Too far, and ice locks a world into stillness. Earth sits within this zone, a fortunate orbit around a modest star, a place where chemistry could stir and eventually consciousness could emerge. It is no exaggeration to say that stars shape the possibility of life itself. This principle extends outward into the galaxy. If planets are common, then so are habitable zones. And if habitable zones are common, then perhaps life is also. Not every star will host an Earth-like world. Many are too massive and short-lived, burning out before life could ever begin. Others are too small, locking planets into orbits where one side bakes in eternal light, while the other freezes in endless night. Yet even if only a fraction of stars carry suitable worlds, the sheer numbers, hundreds of billions of stars, and trillions of planets mean the potential is vast. Somewhere, under another sky, life may already be gazing upward, wondering the same things we do. The thought is both humbling and exhilarating. It reminds us that our own story is not isolated, but part of a cosmic pattern. Just as stars form, live, and die across the universe, so too may worlds sprout, host oceans, and perhaps bloom with life. To call stars the architects of worlds is not just metaphor, but reality. They set the stage, provide the materials, and establish the rhythms that define whether planets become barren rock, gas-shrouded giants, or cradles of life. Each star carries with it the possibility of worlds, and each world carries with it the possibility of stories. Even when we look up and see only stars, we must remember that each light in the sky is not alone. It is part of a system, a family, a structure far more complex than its distant glow suggests. Around Sirius, Vega, or Betelgeuse, unseen planets may orbit. Around the dimmest red dwarfs, hidden worlds may circle, small but real. The night sky is not simply scattered with stars, but with countless unseen companions, each circling silently, each one waiting to be found. The discoveries continue. Telescopes scan the sky for dips in starlight, signs that a planet has passed in front of its sunday. Others measure the subtle wobbles in stellar motion caused by orbiting worlds tugging gently at their parent stars. From these faint signals, entire systems emerge, charted across light years, their secrets carried on beams of starlight that have traveled for centuries. Each new detection is a confirmation of what we now know to be true. Planets are everywhere. When you stand under the stars, it is easy to feel alone, a single consciousness gazing upward into immensity. But in truth, you are surrounded not only by suns, but by worlds. Some are fiery, some frozen, some unimaginably alien. Some may carry the chemistry of life, waiting for time to shape it. Some may have already awakened to it. The stars are not just lights in the sky. They are builders of worlds, guardians of possibility, and perhaps, unknowingly, the keepers of countless other homes. And so, the night sky grows fuller, not only with the stars we see, but with the worlds we cannot. Every point of light carries more than its glow. It carries companions, hidden and circling, silent witnesses to the vastness of creation. The stars shine, and around them, planets turn, and together they remind us that the universe is not empty but overflowing. The stars feel eternal to us. We look up and see them night after night, steady and unchanged. And it is easy to believe they will always be there, glowing forever above the turning earth. Yet the story of stars is not infinite. It has a beginning, it has a middle, and it will have an end. Even the cosmos itself is caught in this cycle, born in brilliance, destined to fade. The stars we know today are only one chapter in a much larger arc, a brief moment in a history that stretches across trillions of years. To think about the future of stars is to think about the future of everything, because without them, there is no light, no warmth, no worlds, and no life. When the universe was young, stars were born in great abundance. Galaxies blazed with star-forming regions, vast clouds collapsing and igniting in bursts of creation. The first stars were massive, short-lived giants, burning furiously and exploding quickly, seeding space with the elements needed for later generations. Over billions of years, the rate of star birth has slowed. The raw material hydrogen and helium gas has been gradually used up, locked into stars and planets, or blown away by winds and explosions. The galaxies still form stars, but at a slower pace than before, like a fire beginning to run out of fuel. Eventually, star formation will dwindle almost to nothing. The cosmos is still alive with light, but the embers are cooling. The stars that exist now will continue to evolve according to their masses. The largest will end their lives in supernovae within a few million years, brilliant but brief. Medium-sized stars like our Sun will swell into red giants, cast off their shells, and fade into white dwarfs. But the smallest stars, the red dwarfs, follow a different path. They burn slowly, carefully, their fuel lasting not billions, but trillions of years. These faint, cool suns are the most common stars in the universe, and though few are visible to the naked eye, they are the quiet future. Long after stars like our Sun are gone, long after galaxies cease forming new generations, red dwarfs will still shine. They will be the universe's last lanterns, glowing gently in the dark for epochs beyond imagination. Imagine a time trillions of years from now, when all the bright, hot stars have vanished, when the spiral arms of galaxies have thinned into dim clouds of remnants. In that distant era, the sky will no longer sparkle with the brilliance of blue giants or supernovae. Instead, it will be filled with the faint red light of dwarf stars, each one steady, each one carrying on its quiet burn. These will be the final suns, holding on to their fuel for as long as physics allows, flickering at the slowest pace possible. The universe will no longer be youthful and bright, but it will not yet be dark. The red dwarfs will carry the torch of starlight for unimaginable spans of time. Even these stars, though, cannot last forever. Eventually, their hydrogen will be consumed, their light will fade, and they will cool into black dwarfs, dense, cold remnants, invisible to all but touch. By then, the universe will be a gallery of shadows. White dwarfs long since cooled, neutron stars silent, black holes wandering like dark seeds. The grand cycle of fusion that powered the stars will have ended. What remains will be the quiet aftermath, a cosmos in twilight. It is almost impossible to hold such timescales in the mind. We think in years, in generations, in centuries at most. But the universe writes its story in billions and trillions, across spans so vast they make human history seem like the flick of an eyelid. And yet, within that immensity, the message of the stars remains clear. They remind us that nothing, however bright, is permanent. Even the mightiest suns must give way to change. And at the same time, they show us endurance, because even fleeting lives can shape the cosmos. The short-lived giants forged the heavy elements, the sun cradles life on Earth, and the red dwarfs promise a future that will outlast everything we know. When you look at the stars tonight, you are seeing a mixture of ages and fates. Some may already have died, their light only now arriving across the gulf of space. Some are still young, with billions of years ahead. Others, faint and hard to see, may burn long after every visible star has gone dark. The night sky is a patchwork of beginnings and endings, layered together in one present moment. It is both fleeting and eternal, both fragile and enduring. The future of stars is not something we will witness, but it is something we can imagine. It is a story of light gradually fading, of brilliance giving way to embers, of embers giving way to shadow. It is also a story of transformation, because even in their deaths, stars leave behind the seeds of what comes next. The atoms of our bodies were forged in ancient stars that lived and died billions of years ago. The fading of stars does not mean the fading of meaning. Their endurance and impermanence are part of the same truth. All things change, but all things leave echoes. Perhaps that is what makes thinking about the future of stars so moving. It is not just about distant physics or numbers too large to fathom. It is about the reminder that everything is part of a cycle, that brilliance and decline, creation and fading, are natural parts of the same whole. Stars light the universe, and in time, they surrender that light. But until then, they burn, and they burn for long enough to give life, to give beauty, and to give us the chance to wonder. One day, the stars will all go dark, but tonight, they shine, and that is enough. When you look up at the night sky, it feels natural to think of the stars as something separate, distant, unreachable. They seem to belong to another world entirely, blazing with a brilliance that has nothing to do with the small details of our lives. And yet the truth is the opposite. The stars are not strangers. They are family. Their lives and deaths made us possible. The atoms that make up your body, the very fabric of your bones, blood, and breath, were forged inside stars that lived and died long before the sun was born. You are not only looking at the stars when you gaze upward, you are looking at your ancestors. Consider carbon, the backbone of all life on Earth. Every chain of DNA, every leaf, every breath of air exchanged in a forest exists because carbon atoms link and form the chemistry of life. Those atoms were created in stellar cores, born in the fusion processes of stars that fused helium into heavier elements under unimaginable pressure. Oxygen, too, the element that fills your lungs with every inhale, was built in the same crucibles, forged from the alchemy of dying stars. Even the iron in your blood, which carries oxygen to your cells, was produced in the furious heart of a supernova, where the energy was so intense that elements heavier than iron were created and cast outward into the galaxy. Every part of you carries the imprint of a star's life and death. It is easy to think of this in abstract terms, a poetic metaphor, but it is literal. The calcium in your teeth, the potassium in your nerves, the phosphorus in your DNA, none of it was present at the beginning of the universe. In those earliest moments after the Big Bang, only the simplest elements existed: hydrogen, helium, and traces of lithium. Everything else came later, cooked in the furnaces of stars and released in their endings. When those stars exploded, they scattered their enriched guts across space, seeding clouds with the materials for new suns, new planets, and eventually, new forms of life. Out of that debris, our solar system formed. Out of that debris, you formed. This means the story of your body is inseparable from the story of stars. The particles that compose you are ancient travelers, once pressed in the core of giants, once flung across interstellar distances, once gathered into the cloud that became Earth. They were here before you, and they will remain long after. To be human is to be a chapter in the story of matter, a continuation of processes that began billions of years before life ever arose on this planet. You are not apart from the stars. You are a way for the stars to look back at themselves. Think about iron again. Every drop of blood coursing through your veins carries atoms that were born in the instant of a star's collapse, an event so powerful it could be seen across galaxies. The iron's journey did not end there. It drifted, joined with other elements, and was pulled into the forming Earth. It cycled through oceans and rocks, moved through plants and animals, until finally it became part of you. The very thing that keeps you alive, that allows your body to breathe, is the gift of a star's death. In every heartbeat, you carry the memory of cosmic fire, and so the stars are not simply above you, they are within you. They are your inheritance, your origin, your foundation. When people once told stories of God shaping humanity from clay, they were reaching for a truth, that we are molded from something older, something elemental. Science has revealed what myth intuited. We are not clay, but stardust. Not shaped by hands, but by gravity, fusion, and time. The miracle is no less profound for being real. This understanding does not make the stars less mysterious. If anything, it deepens the wonder. When you look up at Orion, or at Sirius blazing in the winter sky, you are looking at cousins of the stars that birthed you. Their light may be new to your eyes, but the matter they cast into the universe long ago is what allows those eyes to exist at all. You are bound to them, not just by imagination, but by substance. You carry them in your skin, your breath, your bones. It also means that when stars die in the future, when red dwarfs glow softly in a universe trillions of years from now, the elements they release may one day become part of beings we cannot yet imagine. The cycle will continue, matter reshaping itself, stories unfolding in different forms. Just as you are built from the stars of the past, future life will be built from the stars yet to come. The connection is endless, bridging not only space, but time. To think of yourself this way is both humbling and comforting. You are small, yes, but you are also vast. Your body is a mosaic of the universe's history. You are billions of years old in the atoms that compose you, even if your consciousness is new. You are temporary in form, but not in essence. The matter that makes you will go on, recycled endlessly, part of the stars and worlds that will follow. Impermanence becomes less frightening when you understand that nothing is truly lost. It only changes form, just as the stars themselves do. And so when you look at the night sky, remember this: you are not gazing at something separate. You are gazing at family. The stars above and the stars within you are the same. They shine in different ways, but they are bound by origin. Every flicker of light in the heavens is a reminder of your own story, written long before you were born, continuing long after you are gone. You are stardust. You always have been. You always will be.